In today's lecture, we will see third law of thermodynamics. In the previous lectures, we have seen in detail first law of thermodynamics, second law of thermodynamics, Gibbs function, Helmholtz function, and the Gibbs-Helmholtz equation, and the significance of the Gibbs function, Helmholtz function, and the significance of Gibbs-Helmholtz equation. In today's lecture, we will discuss with the third law of thermodynamics. So, it is known that it is impossible to attain the temperature 0 Kelvin, and the approach to within 1 into 10 raised to minus 6 degrees of absolute zero does not mean that there remains only a small step which will be soon taken. On the other hand, it is practically unattainable. That is, we have to attain 0 Kelvin temperature. This is practically unattainable. In cooling by means of isothermal magnetization and adiabatic demagnetization, the temperature obtained in each stage steadily decreases. If, however, a perfect reversibility is achieved, we would attain absolute zero at the limit of an infinite series of steps. We therefore postulate the third law of thermodynamics as a generalization and can be stated as follows. The first form of third law of thermodynamics is, it is impossible by any method, no matter how idealized, to reduce the temperature of any system to absolute zero in a finite number of operations. And we know that during the 19th century, the first and second law of thermodynamics were formulated and applied to many problems of scientific nature. The first and second law have led to the development of the concepts of energy content and the entropy. The investigations constituted the third law of thermodynamics in the 20th century, and this law, however, differs from the first law in the respect that it leads to no new concepts, and it, however, places some limitations upon the value of the entropy, and it was due to this fact that some writers hesitated to refer it to as a third law of thermodynamics, and it is deduced as limit of delta Cp is equal to 0, that is Cp is the molar heat capacity. So, we will see the next statement of the thermodynamics third law. So, third law of thermodynamics, the statement we will see first. The entropy of pure perfectly crystalline substance is 0 at 0 Kelvin temperature. This is our main statement of the third law of thermodynamics, and initially we have seen one statement which is related to the temperature which can be attained to the 0. So, we cannot attain exactly 0 Kelvin temperature. It is impossible by any method, no matter how idealized, to reduce the temperature of any system to absolute zero in a finite number of operations. And the third law of thermodynamics allows us to calculate an absolute entropy. So, this is our statement. So, introduction of the third law of thermodynamics. The scientist Nernst work on heat theorem and electrochemistry has a very great impact on the physical science, and he was one of the great pioneer of the physical chemistry. In one lecture which he was delivered at Oxford in 1937, he said that It had taken 3 people to formulate the first law of thermodynamics, 2 people for the second law of thermodynamics, but that he had been obliged to do the third law all by himself. He added that it followed by extrapolation that there could never be a fourth law, only third laws will be there. Nernst in 1864 to 1941, this is his lifetime. He is a German chemist and awarded by the Nobel Prize in 1920 for his work in the thermochemistry. And the first and second laws of thermodynamics have led to new concepts of energy content and entropy. The third law, however, does not lead to any new concept, and it only places a limitation of the value of the entropy of a crystalline solid substance. And some scientists does not accepted this law as a third law. They were thinking only 2 laws will be there. And we have seen this statement, the entropy of pure perfectly crystalline substance is 0 at 0 Kelvin. Now we will see the absolute entropy. So the entropy of a substance at a temperature must be greater than its entropy at absolute 0. And yes, it's called as absolute entropy of a substance at temperature T. Sometimes the symbol S can be written as S and suffix to it is a temperature T. So, ST is called as absolute entropy of a substance at temperature T. And the absolute entropy of a pure substance at a given temperature is the sum of all entropies, and it would acquire on warming from absolute 0, where entropy is equal to 0, to the particular temperature. And the entropy change of a system due to only to a small pressure change for a process near 0 Kelvin may be expressed as delta S is equal to integration of ds divided by dp at a constant temperature into dp. And a new equation is also there. St minus S0 is equal to integration of Cp dt divided by T. Here St is the absolute entropy and S0 is the initial entropy at the 0 point. And now the next definition is the molar entropy. So, one way of calculating the change in entropy delta S for a reaction is to use tabulated values of the standard molar entropy S0, which is the entropy of 1 mole of a substance at a standard temperature of 298 Kelvin. So, this is our definition. Molar entropy means what? Is the entropy of 1 mole of a substance at a standard temperature of 298 Kelvin, and the molar entropy is given by notation S0 and units are joule per mole per Kelvin. Unlike enthalpy or internal energy, it is possible to obtain absolute entropy values by measuring the entropy change that occurs between the reference point of 0 Kelvin and the temperature will be 298 Kelvin. And the standard state entropies, one way of calculating delta S, as I have said, the molar entropies are given in the table. So, which is the A0 is the entropy of 1 mole of a substance under standard conditions when pressure is 1 bar. And often the standard molar entropy is given at 298 Kelvin and is often demarked as a delta H0, which is equal to 298. And the units of entropies are joule per mole per Kelvin. Unlike enthalpy or internal energy, it is possible to obtain the absolute entropy values also by measuring the entropy change that occurs between the reference point of 0 Kelvin and the 298 Kelvin. And the correlation between the physical state and the absolute entropy is illustrated in the figure, which I will show you in the next slide, and which is generalized plot of the entropy of a substance versus temperature. So, we will see the plot of entropy versus temperature. So, see, here is the entropy on the y axis and the temperature is on the x axis. So, initially I have taken solid, and solid has a regular arrangement. Each and every particle is arranged in a regular manner, and here entropy is less because there is a orderness is there, no disorderness is there. Therefore, entropy change for the solid is very less. This is called as a fusion. Then when this solid, after heating, it will get converted into the liquid, and there is a liquid in which the entropy will be greater than the solid, because this orderness is get decreased by applying temperature. That is why here is a randomness, but certain randomness is there, not much. After that, the gaseous state is there, means when again we can heat the liquid, it will converted into the gaseous state or the vapor state, and this gas contains the number of molecules which are dispersed. The intermolecular force of attraction between these molecules is very less. Each and every molecule is in the random motion. So, the entropy of the gaseous molecules, gaseous atoms, particles will be much higher as compared to solid. So, our entropy change or the fusion entropy change is very less than the liquid state than the gaseous state. That means the entropy of the gaseous state is much higher than the liquid than solid. So, we will see a molar entropy order as molar entropy of gas is greater than molar entropy of liquid, which is greater than molar entropy of the solid. And there is a relation of molar entropy and the molar heat capacity. Under constant pressure conditions, the molar entropy of the gas can be expressed in terms of the molar heat capacities of the solid, liquid and the gaseous forms, and the enthalpies of fusion and the vaporization. On the basis of this diagram, I have written one equation. So, SMT. So, S and M. S is the entropy, M is the molar, and T represents the temperature. So, we can say that ST directly this, and this is also known as the absolute entropy. So, the absolute entropy is equal to molar entropy at 0 Kelvin, which we have taken, plus integration of Cpm, that is the molar heat capacity at constant pressure, into dt divided by T for solid, means molar heat capacity of a solid, then plus delta H of fusion divided by Tf. Then delta H represents the enthalpy change for fusion process, and Tf is the temperature of fusion. Solid will get fused. After that, plus integration of Cpm into dt upon T for liquid, molar heat capacity for liquid, plus delta H vapor state divided by Tb. When liquid will get converted into vapor, obviously there is an enthalpy change of vaporization divided by boiling temperature, that is Tb, plus again for third, first for solid, second for liquid, same for gas, integration of Cpm into dT by T for gaseous system. Cpm represents the molar heat capacity at constant pressure and here is the temperature change dT by T. So, this is the equation of absolute entropy in which molar heat capacity and the molar entropies are included. Now, molar entropy increases with the disorderedness or the size, then it increases with the number of degree of freedoms and it increases with the number of atoms. When number of atoms will increase, entropy will increase, there is a randomness, there is a freedom, obviously molar entropy will be greater. So, as I have written here, number of degree of freedom increases, molar entropy increases, so that we can get idea about the number of degree of freedom. So, for that we can see the vibrational modes, how this can be calculated. So, vibrational modes can be calculated by this way. For non-linear molecules, we can calculate the vibrational modes by using equation 3n minus 6. N is equal to number of atoms included in a molecule. Then linear molecules, for that 3n minus 5. So, n means number of atoms. By using these two formulas, we can calculate the number of degree of freedoms or the vibrational modes for the molecules. As the vibrational modes will be greater, molar entropy will be more. Then the entropy of all substances is monoatomically increases as a function of temperature. And now the one definition again which is related to the entropy, this is the residual entropy. And according to the law, the entropies of solids should become equal to 0 at 0 Kelvin. This is our third law. But it is observed that the entropies of the substance such as carbon monoxide, water, NO, NO2 etc. are not 0 at 0 Kelvin. And these finite entropies are called as a residual entropies. Means entropy of any pure crystalline substance at 0 Kelvin will be 0, but this is not for CO, H2O, NO and NO2 substances at 0 Kelvin, and this entropy is called as a residual entropies. And this existence of residual entropy in a crystal at 0 Kelvin is due to the alternative arrangements of the molecules in the solid. And now we will see the importance of the third law of thermodynamics. So, these are the 3 points. Third law of thermodynamics helps us in calculating the thermodynamic properties. Then it explains the third behavior of solids at very low temperature, and it helps in analyzing chemical and physical equilibrium. And from this lecture we can conclude that if the entropy of every element in its most stable state at T is equal to 0 is taken as 0, then every substance has a positive entropy which at T is equal to 0 may become 0 for all perfect crystalline substances. Means that we can conclude that for every element, the element should be in stable state and temperature will be 0. Then the entropy of such a substance will be equal to 0 and the entropy of the substance will be positive only at T is equal to 0, and this is for all perfect crystalline substances.